All right, so I've quickly moved around Campbell Hall a little bit and found a new position to finish up here. It won't be too much longer, I think. When I had to quick pick up stakes and move, I had just listed out the system of prefixes that we use as part of naming our covalent compounds. And so the model for naming a covalent compound is a prefix, a first element name, a prefix, the second element name with IDE as the suffix of that element, of that name. So all of our covalent compounds end in the same IDE. We won't have to worry about polyatomic ions as part of this system, actually. Just think about that from a logical perspective. Polyatomic ions, they can't participate in the covalent system, right? So they're excluded from that. So let's go through some of the some simple ones for naming these. All right. I'm going to pick just sort of some random stuff here. How about SCl2, SF4. Sulfur does some nice variations in its naming patterns. Okay. BRF5. N2O4. All right. May need a little more room than that, so let me mark that over here a little further. N2O4. P3S8. Okay. And how about N2S? Again, there are fewer elements that are nonmetals, and covalent compounds are made exclusively of nonmetals. Nevertheless, there are actually more covalent compounds in existence than ionic compounds because of the diversity in the ways that they can put themselves together. As we just saw with ionic compounds, there's only really one formula that can result when an element like sodium bonds with an element like oxygen, or when potassium bonds with oxygen. The only exceptions are those few bivalent metals that we looked at. But that's not true with these nonmetals. They can share their electrons, or it's really a tug of war for electrons, as I mentioned in class last time, in many different ways, and that leads to the great diversity of formulas that we might encounter. All right. So let's name each of these. So SCl2, we have one sulfur, but we do not use the prefix mon ever to start a compound's name. So this is simply called sulfur dichloride, right? There's our model, prefix except mon. We don't use it for the first element. Name the entire element sulfur. A prefix to tell me how many of the next element there are. 2 chlorine, so that's di. The root of the name chlorine, chlor, and then the IDE suffix. Okay. All right. So this next one again has sulfur, but now it has 4 fluorines, and tetra is the prefix for fluorine. So this would be sulfur tetrafluoride. As with the names for ionic compounds, these are not proper nouns, so they are not capitalized, and that would be an inappropriate mechanism to capitalize them. Right? This next one, we have bromine as the first element. I was about to say as the cation. Sometimes we think of this as the cation position, but remember, these aren't ions actually, so it's not really proper to call this the cation. And then in the second position, we have fluorine. We have 5 fluorines. Penta is the prefix for 5. So that would be bromine pentafluoride. In our second column, now we have this, multiple atoms of the first element, so we're going to need the prefix here. So this would be called dinitrogen, and then tetraoxide. Sometimes you'll see a little bit of ambiguity and a little bit of argument, to be honest, in the scientific community as to whether this should be tetroxide or tetraoxide. So really whether that A belongs there or not. There are some grammatical arguments over whether the two vowels belong together or not. Our book acknowledges it's okay to go ahead and do that. I think it's a shift in what's being considered acceptable. So just go ahead and use the prefix and use then the full name like you should, oxide. And don't worry about any truncation of the prefix. All right. Our next one, we have 3 atoms of phosphorus. So tri is the prefix, phosphorus. And then we have 8 sulfurs, so octa sulfide. Again, sulf being the root of sulfur, IDE the standard suffix. And then our last one here is dinitrogen. We do have 1 sulfur, so now we need to say monsulfide. Okay? So here is a case where you use a mon when it's the second element in the formula with a quote anion. Then it's okay to go ahead and use the mon as part of the name. All right. One little note: N2O4. That would never be the formula of an ionic compound, right? Because it's not reduced. But these are covalent compounds, and so we're going to see their actual true molecular formulas. How many atoms are actually present? And so that would be, it would be inappropriate for you to reduce that to NO2 because nitrogen dioxide is in fact a different compound from dinitrogen tetroxide. Both of these things exist. And so we need both formulas, and we don't want to reduce the N2O4 down to NO2. Okay? So that's how we come up with the names of covalent compounds. The formulas are pretty straightforward, almost easier than the names. The formulas, we simply take the prefixes that are part of the names and use them as the subscripts. So the formulas of covalent compounds. You simply use the prefix to determine the subscript of each element. Okay? And then a little special caveat, because these are molecular formulas, you do not reduce. Okay? Unlike your ionic compounds where you need to reduce to the lowest whole number ratio, you do not reduce the formulas of these compounds. Right? So if we had diphosphorus, trioxide, right? Or if we had tetraselenium, heptaiodide, or if we had something as simple as carbon monoxide, we simply turn each of these prefixes into the number that we associate with them, 2 and 3. So this would be P2 for the diphosphorus, O3. Tetra is 4 hepta is 7. So for selenium, the symbol is Se4. Iodide is I7. Se4I7. Carbon, no prefix. So that implies there's only one carbon. And then mon also means 1. So this is CO, carbon monoxide. Right? So the names of, or the formulas of covalent compounds are pretty straightforward. You just take the numerical prefix and it becomes the subscript for each respective element. Okay? All right, that leaves us with one other category to look at. This category is actually a little bit confusing, all right, on the one hand. It is the class of compounds that we call acids. Acids are covalent compounds, on the one hand, with hydrogen as the, quote, cation. Now, the reason they're kind of different from all the other covalent compounds, it's more a topic that we take up in chemistry too, but what happens with these is they tend to give away the H easily. And so then they do result in ions when they're in water. I'm going to add to that. They tend to give away the H easily in water. So as a compound by themselves, they are molecular in nature, or covalent. But when we put them into water, they give up their hydrogen, and then they're like an ionic compound at that point. So they're totally different beasts, so to speak, and we have a different system for coming up with their names. All right? First, we have to decide which type of acid you are. It depends on whether the acid is what we call binary, heard that term earlier in the video class, or ternary. And it means the exact same thing in this context, being binary or ternary. Binary means that there are only two elements. Now, if one of them is hydrogen, to be an acid, it's hydrogen and one other element. Ternary means 3 or more elements. But again, hydrogen must be one of them, and it turns out that the other elements are always put together as one of a polyatomic ion, one of our polyatomic ions. All right, so this is the distinction between binary and ternary acids. And again, there's a different system that I'm about to show you for coming up with the names of these. And so it's really important, just like determining if something's ionic versus covalent, we have to recognize if it's ternary versus binary once we understand it's an acid. Okay? So let's look at the binary first. Binary acids. The name will follow this pattern. Hydro is always the first part of the name. The root name of the other element. And then the suffix IC and the word acid. Okay? So there's a pattern here. All of the binary acids are hydrogen and one other element. Okay? So HCl, H2S, HBr, technically these should be written, by the way, with an AQ after them. That AQ indicates that this substance is in water. All right? That's when these compounds behave as acids. All right? Technically that AQ should always be there. All right? Just as a redundancy to remind you that these things are acids there. Okay? So HCl, it's a binary acid. It is called hydrochlor, as the root of chlorine, ic acid. The hydrochloric part is all one word because hydro is a prefix, the root, and then the suffix ic. And then there is a space between hydrochloric and acid there. H2S is, again, hydrosulfuric. For some reason, sulfur gets sort of special treatment. Instead of just being sulfic, like it's sulfide in compounds, we revert to the entire name, sulfuric there. Okay, so hydrosulfuric acid. And then for bromine, in our last one, it's hydrobromic acid. Okay? So this is the model for all your binary acids. Hydro blank ic acid. Right? And you're going to appreciate that. That word hydro, when you hear the name of an acid, is a dead giveaway. It's part of the name of a binary acid, but not part of the name of a ternary acid. So again, it's a signature difference that you can capitalize on to immediately recognize the type of acid you have. So let's look at ternary acids. The names of ternary acids, again, they all involve polyatomic ions. Okay? And that's important to recognize because the name is going to be derived from the name of the polyatomic ion. So the model for the name of all polyatomic ions is the ion's name with a suffix that depends on the name. Okay? So it gets kind of split. IDE endings become OUS acid. Sorry. Very important. Sorry. Typo there. ITE ending. ITE, right? Almost all of our polyatomic ions end in ite or ate. ITE becomes OUS. OUS. ATE becomes IC. Ic acid. All right? I always remember it as it sounds, you put it all together, kind of like a gross disease, right? Adic-itis. Adic-itis. All right? But it's something you want to get in chemistry. You want to get adic-itis so that you can remember how to name your acids. Okay? So let's pick some of our polyatomic ions. The sulfate ion forms an acid with hydrogen, H2SO4. The nitrate ion forms an acid with hydrogen, HNO3. The chlorate ion forms an acid, HClO3. Again, these technically should all be aqueous, AQ. Right? So the model for naming these is simply to take the ion's name, so sulfate, and change it from ate to ic. Now a sulfur, bad case to start with. Just like down here though, it needs to be sulfuric acid. Look how similar that name is. Sulfuric acid, hydrosulfuric acid. All right? The only defense that we have against keeping track of these two is that word hydro. So you can't use the word hydro. You can't just always think it's there. It's only part of your binary acids, not your ternary acids. All right? And it's really important. It has meaning whether you use that prefix hydro or not. Okay? The next one, we have the nitrate ion. Nitrate becomes nitric acid, right? So sulfate was the ion here to ic. Here it's nitrate, again, to ic. The last one we have is the chlorate ion. So again, it's going to become ic. So this is called chloric acid. And again, like the sulfuric acid, how similar its name is to a very common binary acid, HCl, hydrochloric acid. All right? Let's look at some ite cases. All right? Of course, we had the ClO2 ion. So that would form HClO2 aqueous. All right? We could have the SO3 ion, which would form H2SO3 aqueous. All right? And what if we had the ClO ion? Okay? So ClO2 is the chlorite ion. So this becomes chlorus acid. The ITE is replaced with the OUS suffix, and then the word acid. Still no word hydro though, right? The lack of the word hydro is part of the system actually. All right? SO3, we see that polyatomic ion here. That's the sulfite ion. So this just becomes sulfurous acid. Again, with sulfur. Phosphorus is the other element that's in this category of kind of being a little weird. If you had phosphate, it would become phosphoric acid. All right? You go a little bit more, the root name is involved there. Okay? And then this last one, ClO, is the hypochlorite ion. Remember, this is part of that family that had 4 different ions in it. So we need to say even less oxygen than the chlorite ion. So it's called hypo. So this one sounds a little bit tricky because it's hypochlorous acid. But the hypo is actually, remember, part of the name of the polyatomic ion. Hypochlorous acid. All right? Sounds similar to hydro. Sorry about that. It's one of the little wrinkles maybe of this entire system that we have there. Okay? So that's how we come up with the names of our acids. As far as the formulas go, well, we actually already can come up with the formulas. We find the formula of acids using the Ionic system. Okay? The little thing to remember is that H is a +1 ion in that system there. Okay? So if you wanted to find the formula of hydrofluoric acid or of, let's say, nitrous acid, okay? Hydrofluoric, that's telling you this is a binary acid that has hydrogen as one element, +1, fluorine as the other element, -1. What do we do in the ionic system? We switch those down and we end up with just HF as the name, or as the formula, sorry, and then we should put an AQ after it to indicate that it's an acid, another part of that name. Nitrous acid, on the other hand, we're lacking the word hydro here. Bing, bing, that's an indication that there's a polyatomic ion here. The us comes from having been the ite ion. So we're looking for the nitrite ion. That would be NO2 with a 1 minus charge. All acids have H1 plus. So we switch those down, and we end up once again with HNO2 then, aqueous. Again, no parentheses would be needed here because there's only one unit of the nitrite there. Okay. One more. How about carbonic acid? Carbonic acid comes from the carbonate ion. 8 comes from ic. The carbonate ion is CO3 with a 2 minus charge. Acid means that hydrogen is the cation. Switch those down. We need 2 hydrogens to balance the 1 carbonate ion. So H2CO3 is the formula of carbonic acid. All right. Very productive session today. I think I've kept you an extra 5 to 7 minutes. Sorry about that. I was excited about all this material that we have here. So we're in great shape, I think, right now. We've covered all of the systems of naming and coming up with formulas for ionic compounds, covalent compounds, and now acids. So we'll pick up with that next time I see you in class, which will be on Wednesday, September 27th. If you have any questions about anything that we've covered in the video, feel free to ask me right at the start of class, and I'd be happy to review the material with you briefly before we move on with our next steps, which is now to look at the mole again, but to do so for formulas and compounds now, rather than for just atoms and elements. So until I see you then, I hope you're doing well, and I'll see you in class next time.